Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMathInstruction. Today, we're going to be doing Unit 5, Lesson number 3 on summation notation. It's even just fun to say summation notation. So let's get right into it because there's really no way to summarize this without just jumping into it. Many times in math, we need to add a bunch of numbers that are in a list. And that's what summation notation is all about. It's sometimes called sigma notation, and those of you that go into college math, not being a math major, you just take any math at the college level, will see sigma notation all the time. This large, almost E-like looking figure is the Greek letter sigma, and that's why you'll hear me refer to it sometimes as sigma notation, and you'll hear math professors refer to it as sigma notation. A lot of students refer to it as that giant E. All right, it's not an E, but whatever. All right, so let's look at it because this just is weird looking. All right, so first let's talk about I. I is what's called the index variable, and it's literally just moving you along. It's kind of like when you've got sequences. It's your place in line, okay? A always starts at this value and ends at this value. And those values are always integers. They're always whole numbers. Now, they can be negative. That's okay. This isn't a sequence, all right? You can have negatives, but you can't have fractions. And then what happens is you just go up by ones, all right? So it allows us to basically say, hey, I'm going to add up this giant list of numbers. Okay, now what is the list of numbers? How do we know what the numbers are? Right? We'll find that out in the first set of exercises. So let's see how sigma notation works. I'm going to clear this out and let's jump right into it. All right, it says evaluate each of the following sums. So let's look at this. This is just our function. And yeah, it's a function of the variable I, but that's okay. Now what sigma notation says is I starts at 3. So what I'm going to do is I'm going to do 2 times 3. And then I'm going to do plus. Then I'm going to move that up by 1. And I'm going to do 2 times 4. And then I'm going to do plus. And then I'm going to move it up by 1. And I'm going to do 2 times 5. And then I'm going to stop. Okay, and I'm going to stop because that's my stopping input. This is my start. This is my stop, and now I just have to do the sum. 6 plus 8 plus 10 gives me 24. All right, that's not so bad. Sum up a bunch of numbers. Let's do another one together. All right, this one says, well, my function, I use the letter k. I, j, k are the most common indice variables. And I have to start at -1. So it says take -1 and square it. Then I'm going to move that up by 1, and I'm going to be at 0, and I'm going to square it. Then I'm going to move it up by 1, I'm going to be at 1 and square it. Then I'm going to be at 2 and square it. And then I'm going to get in the way of this problem, but it doesn't care. 3 and square it. And then I'm going to stop, right? Because this is where I start, and this is where I stop. -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4, 13, 14, 15. All right, that's not too bad. Really, it's just all about being told a rule, being told what inputs go into the rule, and then adding up all the outputs. That's it, though. That's really it. I mean, sometimes it can get a little crazy. For instance, let's take a look at this one. This is 2 raised to the j power. It is not 2 times j. So we're going to have 2 raised to the -2, right? Because that's our starting. Then we'll have 2 raised to the -1. Then we'll have 2 raised to the 0. Then we'll have 2 raised to the first. And then we'll have 2 raised to the second. Now we have to remember our negative exponents. 2 raised to the -2 is 1/4. 2 raised to the -1 is 1/2. 2 raised to the 0 is 1. 2, that looks like a 3. I'm sorry about that. That's not good. Sometimes being sloppy doesn't hurt that much, but sometimes it can be really confusing. And now it's just an issue of adding those all up. If you do it with fractions and common denominators, you get 31/4. Or if you do it more like a normal human being and get a decimal, you'd get 7.75. All right. Well, how about this? If you think you got it, pause the video now and try to work on D, E, and F, and then we'll go through them. Don't get frustrated if you get stuck on one. Work on it as long as you feel like you can, and then if you just can't figure it out, move on to the next one. Okay? All right, let's go through them. Letter D, we're taking -1, kind of like this last problem, and we're raising it to the I. So we're going to have -1 to the first, -1 to the second, -1 to the third, -1 to the fourth, and again, -1 to the fifth. Now, -1 raised to integer powers is actually kind of important. Anytime we raise -1 to an odd power, it's -1. And anytime we raise -1 to an even power, it's +1. So that's going to be -1 plus 1 plus -1 plus 1 plus -1. And that leaves me with a -1. Yeah, still a -1. Let's take a look at this particular problem. Here we're starting off with a value of 0. Let's see if we can do some of the substitution on our own, without having to write it all down. If I put 0 in there, I'll have 2 times 0, which is 0, plus 1 is 1. So that's my first term. Then if I put 1 in there, I'll have 2 times 1, which is 2, plus 1 is 3. If I put k equals, say, 0, 1, 2, that's going to be my last one. If I put 2 in there, I have 2 times 2 is 4, plus 1 is 5. And then I'd stop, and I'd get 9. All right, this one I think I'll write out a little bit more, but it's 1, 2, 3, right? I'm going to start at 1, end at 3. So if I put 1 in there, I'll have 1 times 1 plus 1, plus 2 times 2 plus 1, plus 3 times 3 plus 1. So that's going to be 1 times 2, plus 2 times 3, plus 3 times 4. So 2 plus 6 plus 12 gives me 20. Good. So it's not that hard of notation to use when we're evaluating it. There are going to be some tricky things in this lesson, but that shouldn't be one of them. Pause the video now and write down whatever you need to. All right, I'm going to clear it out. Let's move on to the next one. Little multiple choice question. See if you can work through this one on your own. All right, besides the fact that I have some interesting looking changes in fraction bars here, let's do it. We got to put in 1, 2, 3, and 4. So it looks like I've got 1 divided by 1, plus 1 divided by 2, plus 1 divided by 3, plus 1 divided by 4. Right? Now I could do it on my calculator. I can also get a common denominator. It's going to be 12. So I'd have 12 twelfths plus 6 twelfths plus 4 twelfths plus 3 twelfths, 18, 22, 25 twelfths. All right, not too bad. But what's on the back side of the sheet, right? How is this going to get hard? And it's not going to get too bad. There's going to be something a little tricky coming up. Anyway, pause the video now and write down anything you need to. All right, let's clear out that text and move on. Consider the sequence defined recursively by a sub n equals a sub n minus 1 plus 2a sub n minus 2, a1 equals 0, a2 equals 1. Find the value of this. I want you to pause the video right now and look at this entire problem. It's not all that difficult, but there's a lot of mathematical symbolism in it that can get quite confusing. So I want to see if you can weed through it on your own, and then we'll take it from there, okay? All right, let's work on this. Well, I tend to like to work on math problems sort of backwards. And what I mean by that is I want to look at this and really understand what they're saying. I'm going from 4 to 7. 4, 5, 6, 7. So let's just forget about all this. Just forget about it for right now. Right, if I was just evaluating this, I'd put the 4 in and I'd get A4. Then I'd go up and I'd get A5. And then I'd go up one more and I'd get A6. And go up one more and I'd get A7. So really, all this thing is telling me to do is add the 4th through the 7th terms of the sequence. But I only have the first term and the second term. I still need 4, 5, 6, and 7. So how do I interpret this rule? What does this rule say? It says, to figure out any element of the list, I take the previous one and add 2 times the one before that. So let's see if we can do this to get A3. A3 is going to be A2 plus 2 times A1. What was A2? A2 was 1. A1 was 0. So I'll find A3 is 1. A4, on the other hand, will be A3 plus 2 times A2. A3 is 1. A2 is 1, but I have to multiply it by 2, so that'll give me A4 is 3. A5 is A4 plus 2 times A3. So that's going to be 3 plus 2 times 1. That's going to give me 5. Almost looks like the odds here. A6 is going to be A5 plus 2 times A4. A5 is 5 plus 2 times 3 is going to be 5 plus 6 is 11. Well, there busts my odd things. I missed 7 and 9. And I also need A7. A7 is going to be A6 plus 2 times A5. So that's going to be 11 plus 2 times 5. 11 plus 10 is 21. So what the problem is actually asking me to do is add up these. 3 plus 5 plus 11 plus 21. And when I do that, I get 40. Yep, that's right. So summation notation, we'll see, gets used a lot with sequences. Sorry about that, I had something in my eye, and hard to do a video with something in your eye, besides your eye. Anyway, so summation notation is going to get used a lot when it comes to sequences to give us what are known as series. But that's in lessons to come. What we're going to look at next with summation notation is going to be the hardest thing that we do with it. So, pause the video, write down what you need to, and get ready for the tough part. All right, let's clear out that text and see what we've got. Now, undeniably, the hardest thing to do is to express a sum using this sigma notation, right? This is very similar to what we've had in previous lessons where we had, let's say, a sequence, right? Not a sum, but a sequence. And we wanted to be able to write it in terms of a formula. That's very, very similar here. All right, now, one huge difference. None of these answers are unique. None of them. All right, so it's good to check them. And certainly when you look at the solutions to tonight's homework, right, tomorrow, let's assume, you'll see that your answers may not necessarily match the ones that are down there because, again, none of these answers are unique, meaning that there are plenty of correct answers. But let's take a look at the first one. What do we really have? I've got 9 plus 16 plus 25 plus ... plus 100, right? So what's going on there? All right, well, 9 is 3 squared. 16 is 4 squared. 25 is 5 squared. It looks like we are just adding the squares of the whole numbers, which is good. So I can start I at 3, I can end I at 10, and I can just do this. Now you might say, well, that seems like there's only one correct answer. But watch this. Watch me be tricky. Watch this. Let's say I did this. This would still be correct, right? Because if I put 2 in there, I'd get 2 plus 1, which would be 3, squared would be 9. And if I went up to 3, I'd have 3 plus 1, which is 4, squared, and I'd get 16. So this is also correct, right? So there are many, many different answers. Let's take a look at letter B. Ooh. Well, this is definitely an arithmetic sequence, right? Because what's happening is we're adding 3 each time. All right. Now, it's tempting to say, well, I mean, maybe it's negative 6 plus 3i. All right? Because I'm starting at negative 6. But then, where would I start? Right? Because, every one I go along, I should have that. Well, if I want myself to start at negative 6, then I should start at I equals 0. Right? And think about that. If I put 0 in there, right, I'll get 3 times 0, which is 0, plus negative 6 is negative 6. Then if I put 1 in there, 3 times 1 is 3, plus negative 6 is negative 3. Put I equals 2 in there, 3 times 2 is 6, plus negative 6 is 0. So that's working out. The question is, what should be up here? Well, I could figure that out by actually just pretty much solving for it, right? Well, let me just set that equal to 15 and figure out what I would have to be. Well, in that case, 3i would have to be 21, and I would have to be 7. So there it is. And again, one of many that are correct. Oh boy, what is going on with this last pattern? 1/25, 1/5, 1, 5, eventually all the way up to 625. Pause the video and see if you can figure out what the pattern is. Did you figure it out? These are all powers of 5, right? That's 1 over 5 squared, 1 over 5 to the first, 5 to the 0, 5 to the first. 625 happens to be 5 to the fourth, right? Yeah, that's 5 to the fourth. Now what is that? That's actually 5 to the negative 2, 5 to the negative 1, 5 to the 0, 5 to the first. So in fact, we can write this as simply I equals negative 2 to 4 of 5 raised to the I. There we go. Now again, this is tough because it requires us to see a pattern and then turn that pattern into a formula. But remember, you can check it. And if you check it and your formula is not right, try again. See if you can come up with another formula by modifying the one that you had, especially if you were getting results that were close to being right, whatever that means. All right, pause the video now and write down anything you need to. Okay, I'm going to clear it out. So, exercise number 5. Which of the following represents the sum 3 plus 6 plus 12 plus 24 plus 48? Pause the video. See if you can figure out which one is the correct representation. All right, well, this is relatively straightforward because we can literally check every single one of them to see which one gives us that sum. So for instance, on the first one, if we have the summation of I equals 1 to 5 of 3 raised to the I, that would be 3 to the first plus 3 to the second plus 3 to the third plus 3 to the fifth. Well, 3 to the first is 3, certainly, so that's good. But 3 to the second is 9, and 3 to the third is 27. That's not the sum that we have, so that one's out. Let's try this one. The summation of I equals 0 to 4 of 3 times 2 to the I. Well, let's try that. That would be 3 times 2 to the 0 plus 3 times 2 to the first plus 3 times 2 to the second, etc. Now don't forget your order of operations. Do those exponents first. 2 to the 0 is 1 times 3 is 3. 2 to the first is 2 times 3 is 6. 2 to the second is 4 times 3 is 12. Ah, there it is. We got it. All right. Pause the video and we're going to take a look at one last kind of cool summation. All right, let me get rid of this. So some sums are more interesting than others. All right, this one asks us to determine the value of the sum of I equals 1 to 99. All right, of that summation. Show your reasoning. This is known as a telescoping series or sum. So pause the video now. Somehow you can figure out the value of this even though you're adding up 99 terms. So play around with it. See what you get. Look for patterns. All right, let's go through it. Now, when you have no idea what to do, what I always say is do anything you can do. So let's start with I equals 1. We get 1 over 1 minus 1 over 2. That would be the first term. Plus. All right, then if I put 2 in there, I'll get 1 over 2 minus 1 over 3. That would be the next term. All right, I'm not sure I see it yet. The next one, if I put 3 in there, I'd have 1 over 3 minus 1 over 4. And I think I see a little bit of a pattern. 1 over 4 minus 1 over 5 plus dot, 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 plus eventually if I get 99, I'd have 1 over 99 minus 1 over 100. Now keep in mind that addition is associative, meaning all those parentheses are pretty much worthless. I'm going to just write 1 over 1 as 1. I can remove the parentheses, right? I can actually rewrite it like this. And eventually we would have this. This is how it would end. But notice we can now pair these guys off, and all of them are going to 0. That's why it's called telescoping. All of these go away, and eventually we just have 1 minus 1/100th. So all of this adds up to 99 100ths. Isn't that cool? It's called telescoping because all those middle terms just cancel each other out. It's kind of a neat sum. All right, well, pause the video if you have to. Write down anything you need to, and then we'll wrap up this lesson. All right, let's do it. So there's going to be a lot of times in math, both in this course and in future courses, where you're going to want to represent a large sum with many terms, maybe hundreds, thousands of terms, but you're not going to want to write them all out. And yet they exhibit some kind of a pattern. And for that, sigma or summation notation is the way that you want to go, right? Because it expresses sums of as many terms as you want with one little symbol. Now today we were just getting used to the way that symbol works, its conventions, this index variable I, j, k, whatever we have, all right? But in the future we'll need to use this tool. We won't need to just get used to it, okay? For now though, I want to thank you for joining me for another Common Core Algebra 2 lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.